We've talked about uniform linear arrays, which are arrays where the spacing is uniform and the amplitude of the voltage on each element is also uniform. What about a situation where we have uniform spacing still, but we don't have a uniform amplitude excitation? In that case, the array factor can be written in a slightly more general way. We'll write it as the sum from 0 to n minus 1, where big N here is the number of elements that we have total. W sub n, which is the amplitude weight of each element, times the position-related phase factor, e to the j, k, and d cosine theta. Now, if we notice that there's this n in the exponent here, so we could write that as e to the j, k, d cosine theta to the n. Or if we define e to the j, k, d cosine theta to be some variable z, we just write that as z to the n. So now our array factor is actually a polynomial, n equals 0 to big N minus 1, of w sub n, some coefficient, times z to the n. And our choice of those coefficients has a big effect on the shape of that polynomial. Now this polynomial gets evaluated for values of z that are on the unit circle. So the magnitude of z is always equal to 1, but the phase of z can be between it can be between kd and minus kd, like that. And those are equals. If we think about it as a polynomial, there are actually some pretty cool facts about this that can be taken advantage of in order to design the array factor pattern that we want. First of all, this polynomial has n minus 1 zeros. They might not all show up on the unit circle, but it always has n minus 1 zeros. We'll name them z1, z2, z sub n minus 1. We'll talk about those a little bit more. Second point, since in general you can factor a polynomial in terms of its zeros, you could say that the array factor can be written as the very last amplitude weight times z minus z1 times z minus z2 times all of the other ones, z minus z n minus 1, like that. And the magnitude of the array factor is the product. Let me do one slight adjustment here. The magnitude of the array factor at some location z is the product of the distance between that location and each of the zeros. So that would be the distance to 0, number 1. And this next term is the distance to 0, number 2. And then all the way up to the distance to 0, n minus 1. So the further away you are from a zero, from all of the zeros, the larger the amplitude of your polynomial is. This, in fact, always works anytime you can factor a polynomial. And we're working in the complex plane, so you actually can factor it. you are writing it in terms of the distance from its zeros. Visually, if we draw the unit circle as our locus of allowable values for z, and let's say that these are the zeros of our polynomial, at some position on this circle, I'm going to choose this one because it's actually the furthest from all the zeros, the value of that array factor is the product of the lengths of all of these line segments from the 0 to that position. So the max distance from all the zeros tells you where the main beam is. And that means that you can shape the array factor by controlling the locations of the zeros. If you want no side lobes, you can do that by controlling the 0 locations. You can say, well, what if I just put all of my n-1 zeros on this one point? Which would look like z minus z1 to the n-1. Then as long as I keep, whoops, that's not how you write keep. As long as I keep kd less than or equal to pi, then we really only see this 0 in the polynomial. This is actually a standard method of array excitation called the binomial. Now this has some important points that I should make about it. First of all, you need a small value of kd for actually having no side lobes. So the spacing between elements needs to be less than or equal to half a wavelength. Second, it has a really wide main beam. So usually people will choose the largest allowable spacing between elements. So usually you just choose the spacing to be equal to half a wavelength. And that gets you the narrowest main beam and the most directivity that you can actually achieve and still have no side lobes. If, on the other hand, oh, and a third thing, it tends to result in, for a large total number of elements, you can have it results in large current ratios between the elements. So like the middle might have a really large voltage, while the edges have a really small voltage. So it's not especially efficient with the small elements, and you end up wasting some effort and wasting some power in order to get this mathematically very specific excitation that doesn't, and those outside elements contribute to the pattern shape, but they don't do a good job of actually getting power out. On the other hand, you could do something other than the binomial excitation too. We're going to talk a little bit more about the binomial excitation later. But you can also adjust the position of zeros to get equal height side lobes. If you have a standard uniform linear array, then the zero locations are actually evenly split. And they're evenly distributed all around the array. You have a 0 here that cancels out with the 0 on the bottom, so that one doesn't count. And then you might have a 0 here, 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 a 0 here. The side lobes in between the zeros that are higher, that are closer to the main beam, those have a higher side lobe value. And side lobes in between zeros that are further away from the main beam have a lower side lobe level there. So we could adjust that by increasing the amount of space between the side lobes, between the zeros on the back, and decreasing the amount of space between the zeros closer to the main beam in order to get the side lobe level to be uniform all the way around, which is a really efficient way to meet a requirement that your maximum side lobe level has to be such and such. This is also a known solution called the Dolf-Chebyshev array excitation. And this one is actually pretty popular because it gets you the most directivity for a specified maximum side lobe level. So people like that one because it gets you good aperture efficiency. I'm going to talk about the binomial distribution a little bit more first. The binomial excitation. I'm going to talk about the binomial excitation a little bit more first of all. And then in my next video, I will talk about how to do a design with the Dolf-Chebyshev excitation.